What's up, gang? Chem Daddy here.
This is Chem Daddy's first vlog. That will not go on to YouTube.
What? No! That has to be on YouTube.
Okay, so anyway, this is the definition of a complex ion. We've seen complex ions a couple times this year. I've mentioned them, I know. Yesterday in our experiment over here, this indicator action, the one that made the dirty brown color, that was a complex ion too. We had the yellow stuff that you put 6 drops into your flask was iron ion. And when the thiocyanate was added and all the silver got used up, then the thiocyanate stuck onto iron, and we get this. So we have one ion combining with another ion, but it does not become neutral. And since it doesn't become neutral, that's what makes a complex ion. So that's what we have. You have to have a transition metal ion to make a complex ion. So like sodium, potassium, barium, they wouldn't work. It's got to be a transition metal. And then it's got to be something attached to it that has at least one lone pair on it. Now that something attached we call a ligand. The thing with the lone pair is a ligand. Anybody here have experience in AP biology? You've heard of ligands,
Yeah,
right?
so
When?
much it hurts.
What did you do with those?
Well, it's like for bio, it's anything that like binds to something. So like ion channels, if it binds to something, it like open them or close them.
Yep, and it has to do with the same idea. It's the attraction of a lone pair on something combining with the. In the case of a complex ion, the transition metal ion has empty orbitals. Orbitals are places where you can hold 2 electrons around an atom. We'll talk about that when we do electron arrangement. But yeah, the lone pair on the ligand is going to attach itself to the complex ions. Not the complex, the transition metal's empty orbital. Here's an example of the formation of a complex ion. I don't know that you need to write this, but just take a look at it. So the copper ion, here's a transition metal ion, copper plus 2, and it's got 4 ammonia molecules that attach to it. Now each ammonia molecule has that nitrogen that has a lone pair on it. And the lone pair is what causes this to happen. The copper ion has a whole bunch of empty orbitals in it, and that lone pair, each of those lone pairs are going to attach themselves onto an empty orbital. It's called a coordinate covalent bond, when one atom is providing both of the bonding electrons. Did you do any chemistry of that? Do you remember, Srijani? Or
I didn't do that much chemistry.
in bio, yeah, you just talk about, like on the macroscopic level it happens. Okay. So the copper ion winds up with 4 covalently bonded ammonia molecules to it. Now, the copper ion had a positive 2 charge. 4 neutral molecules attached to it, so this whole ion still has a positive 2 charge. So that's our first exposure to, I guess at least one of these. The iron and thiocyanate does the same thing. Now you might have, either now or later, have the question, how do you know how many of the ammonia molecules, why didn't only 1 ammonia molecule do this, or can more than 4 do this? The answer is this. Generally, there are exceptions to this, but what I want you to remember is generally, the transition metal ion, whatever its charge is, in this case it's a positive 2, double that number, that's how many ligands will attach to it. That's something that you want to write down. It's called the coordination number. The coordination number on the complex ion is going to be whatever the transition metal's charge is times 2. No.
You can look it up on
Watch that.
Sorry, the intro.
The number of the, I can't believe that I did that. That is not going on.
No.
Please, I will buy you like 3 pounds of chocolate.
Okay, I'll put it on. Everybody heard that, right?
And it's on.
Oh, it's
on.
Daniel Syed. Yep, got it. All right, so anyway, the number, whatever the charge on the transition metal ion is, double that, that's how many ligands will attach to it. Okay, are we good with that slide? Oh. Now it turns out we're not going to pay much attention to this, but I do want you to know that when you have a transition metal ion and ligands start attaching to it, every ligand that goes onto it is going to have its own formation equilibrium value. We call it a formation constant. Here's a simpler complex ion because you got the silver with only a positive 1 charge, so it's only going to take 2 ammonia molecules, the positive 1 times 2. So when the silver ammonia complex is made, here's the first step. You have just a bare silver ion. It'll take 1 ammonia molecule, and that has a certain K value. Some poor chemist had to spend probably years coming up with what the K values of individual steps of a reaction are. Some things in chemistry are kind of boring.
Sometimes.
You know, just as I said that, I thought, what is my class going to say to that?
We're outspoken.
You never disappoint me.
It's better to be honest than
Yes, it
to
is.
be superficial.
Yep, yep. So anyway, you have the 1 ammonia on the silver. That's got a certain equilibrium constant. And notice what the magnitude of the constant is. It heavily favors the formation of a complex ion. These are very stable structures because you can tell by the K value. Both of these steps in this the formation of the complex ion heavily favor the complex ions, not the other side of the reaction. So if we take these 2 steps and we add them together, we've added chemical equations together before. Sometimes things will cancel out. Does anything cancel out when we add these 2 together? Yeah, this intermediate product here with only the 1 ammonia on it, that will that's formed, and then that has another ammonia added to it and makes the actual complex. So that will cancel out. And we know that when we add 2 chemical equations together, get an overall equation, what we do with our K's? Multiply them together. So now we see that, I don't know why it does that. Silver with 2 ammonias attaching to it is going to have, you know, that normal silver ammonia complex formula. And the K value is that times that, which gives us 1.7 times 10 to the 7th power. So that's a very substantially stable structure.
Why is it stable?
You can tell from the K value that this is a more stable thing than this is because its K is so big. If you remember, this is going to be nerdy. K is huge, so the natural log of K is a big positive number, and R and T are both positive, so this is all a positive. Delta G for sure will be negative, and so spontaneously it will make that, which means that the complex ion is more stable than what it started at. Yeah, it never leaves us.
G.
I can't keep up with all the new talk.
We're just weird.
I never so much saw that generation gap widening until just recently when you know there's like such new vocabulary that's always developed. I'm out.
It's lit savage.
Yeah, yeah. I still don't know if lit is good or bad, but
You can
you'll say it.
You're allowed to use it. You're allowed to use it.
Don't expect me to. So here's this picture of what the silver ammonia complex looks like. I actually do have a demonstration. Sorry, band friends, but I'm going to do it tomorrow. I do want to show you what it looks like when complex ions form. It is pretty cool. And maybe I'll make that installment 2 of my new vlogging program. Go and watch that. But don't count on it. Now here's what I'd like to do. We're going to start with a very simple KSP problem that has nothing to do with complex ions. We're just going to give ourselves a point of reference. What is the solubility of just plain old silver iodide in pure water? Silver iodide is not very soluble. You see what its KSP is, 10 to the negative 16th power. Let's just do this one together. We don't want to mess around with things that we already know how to do. So we're just trying to find the solubility. So if I were to make an ice table, that's nothing because it's a solid. That initially is 0, that initially is 0. It shifts to the right, so that goes down by x and up and up. So at equilibrium, you got x and x. KSP is 1.5 times 10 to the negative 16th. And that's equal to x squared. So all we have to do is take the square root. This thing right there is what they're asking for. The molar solubility is always that. How much of the solid dissolves? So, easy enough to take the square root of this number. X, which is the solubility, is 1.2 times 10 to the negative 8 molarity. Yeah? On the next slide, we'll take the same exact ionic compound, silver iodide, but instead of trying to dissolve it in pure water, we're going to dissolve it in water that has a ligand present. It's going to be an ammonia solution. So we're going to be talking about that silver ammonia complex. Are we good with this? This is pretty simple. Okay, so part B of this. Calculate the solubility of silver iodide if it's in not water, but it's in a 3 molar ammonia solution. So the silver can make a complex ion with the ammonia. The overall formation constant for the silver ammonia complex, and that was just from the previous couple of slides, 1.7 times 10 to the 7th. So there's really 2 reactions that are happening in water when we put the ammonia and the silver iodide into it. The silver iodide is trying to dissociate. It only goes a little bit and then stops. You can tell that from the K value being so small. It's just good.
What is the next beauty quiz?
I'll spring it on you. Maybe it'll be unannounced. Which would be kind of a shame because, yeah, if I didn't announce when reading quizzes were, then you would never know what and when to read.
Right.
Yeah.
So your next reading quiz is unannounced.
Okay. I'm thinking of what to do.
Okay, so here we have 2 different equations happening. The silver iodide is dissociating, small amount. But then what few silver ions we have present, some of them are attaching to ammonia molecules. Now if some of these, look at where I'm pointing, some of these are attaching to ammonia molecules, what's happening to this first equation? Le Chatelier's principle says that if we make some silver and then the silver is gobbled up by some ammonia, the concentration of silver decreases, which causes this to continue dissolving and it'll shift right. That's pretty important to recognize. So let's go ahead and take these 2 chemical equations that are really happening simultaneously and add them together. The silver ion is going to cancel out, and we're going to have this. Silver iodide plus 2 NH3s yields. And then over on the right side, we have our complex ion, silver with the ammonia. No, not 2. With a positive 1. And then an I negative. Adding these 2 together, we can multiply their K values. And let's see, that would be 2.5 times 10 to the negative